Hello, everybody out there on the internet, as well as MIT students. So welcome to today's class on Introduction to Computational Thinking with Julia. And today is Monday at MIT. I know that might seem very strange, but they do this every semester to kind of balance out the Monday, Wednesday, and Tuesday, Thursday, Monday, Wednesday, Friday, and Tuesday, Thursday classes. And so this will be the only time during the semester when Monday will be on a Tuesday. Strangely enough, I've been at MIT many years. Almost nobody ever confuses this. You'd think that this would create a lot of confusion. It actually does not, at least not at MIT. But let's start today's class. So today's class, the plan is to do a quick introduction, kind of, maybe not so quick, but an introduction to dynamic programming. And then what we are going to do is play with that for a really fun application called seam carving. So what I'd like to do in today's lecture is, today I'm going to start by, I have a little demo here of a dynamic program, at least the concept of a dynamic program. And then what I'd like to do is actually illustrate seam carving with an example, and then play with you a fantastic video from last semester when Grant Sanderson gave a lecture on exactly this material, seam carving. I think you're going to love listening to this lecture. I mean, I suppose I could have leave it to you to watch it twice the speed, but I'm telling you, this is one worth listening to at the regular speed. So I hope you'll enjoy it. And then when we're done with the video, if there's still time, and I think there'll still be a little bit of time, we'll play some more with these notebooks. So to begin, dynamic programming. So if you haven't heard of dynamic programming before, I gather that this is a standard example on a lot of interviews, like, if you interview for Google or something, knowing, if they ask you to write code, it's very often you're supposed to recognize that this is a dynamic program. So what is a dynamic program? Well, first of all, the word program itself is kind of misleading. It's rather archaic, but here the word programming means you're solving an optimization problem. You're trying to minimize, or it could be maximize, but in this case, we're trying to minimize something. And so if you've ever heard of terms like linear programs or dynamic programs, the word program there does not mean what you probably think it means. It doesn't mean like writing code in Julia or Lisp or Fortran or Python. It means it's an optimization problem. And dynamic programming is a real staple of, real major part of algorithms classes. And so if you ever take an algorithms class, you'll probably see, an entire segment of your semester just talking about dynamic programming. So here we're going to use a dynamic program. And so it seems sensible to kind of give you a little bit of the feeling for what a dynamic program is. And also, as part of computational thinking, just to show you just how much fun it is to make your own little demo and explore what's going on. So let me phrase a problem. Let's create a matrix. It actually doesn't have to be square, but in this case, I made them square. Let's create a random matrix. I took a matrix here with the digits 0 through 9, if you can see. And if you use the slider, which should be working on the web, you can make the matrix smaller or bigger. I made it go up to 12. You can go higher if you like. I guess 8 makes me think of a checkerboard, so maybe I'll do an 8 by 8 in this case. Here's an 8 by 8 matrix. And what I would like to do is minimize something. So what am I going to minimize? Well, it turns out that there are 11,814 paths on this checkerboard that have the property that here, let me draw some of these paths. Maybe you can see the property yourself. It has the property that as you go from top to bottom, your steps are only southeast, south, or southwest. Okay, so those are your choices. You want to take paths that are south, southeast, or southwest. So let's move along a little bit. So if you can look at the black paths, you'll see that what they all have in common is you're starting at the top and you advance downward one row each time. And as you go downward, it's kind of like a queen on a chessboard moving only downward, right? It can go down, to left and to the right, or southwest, south, and southeast, right? And so all of these 11,814 paths on an 8 by 8 board have this property that they're going south, southwest, and southeast. Okay. And what we're going to do is we're going to add up the numbers visited along the path. For example, on this black path here, you see 0 plus 9 plus 5 plus 3. It's actually listed up here. And for those of you who can't add anymore like me, the sum is 34. And what our goal is to find the path that has the smallest sum. Okay, so does everybody understand? So for example, I'm going to start at the far left. The sum is 1 plus 5 plus 9, adds up to 30. Okay, yeah, it adds up to 30. And at the other extreme, I'll go to the far right. We're going down this way. It adds up to 29. But there is a path. You can see this winner over here. I've kept the winner kind of fixed so you can kind of keep track. Adds up to 12. And the winner, actually, I computed here. So the winner actually for this matrix is number 3899. So if I can sort of move my slider to 3899, you'll see the actual winner. So let's get to 3899, kind of hovering on that. I love playing with this, by the way. So, I mean, I sort of wonder whether it's as much fun for you to watch me as it is for me to press the buttons, but I love pressing the buttons. Maybe the moral of the story is that you folks should absolutely play along and do the buttons as well. So here I lined up the black path with the pink path, and you could see, 1 plus 1 plus 3, 2, 2, 3 adds up to 12. And that will be the minimum on this particular 8x8 board. Of course, if I run this again, I mean, I could get another 8x8 board, and you see the pattern is completely different. Here's the minimum is 39, and it's this path, right? Or I could generate another board, and you could see that this time the path goes this way, and it's 36. Okay, so these are the different paths. I could generate a new board each time just by sliding that slider. Okay, and so the goal is to find the minimum. And obviously one way to do it is to generate all 11,814 paths and add them all up, right? That would be straightforward. That would be a simple naive algorithm, relatively easy to code up, though you'd have to be a little careful when you do the paths that you don't hit the borders, all that usual sort of stuff. But basically fairly easy to code up. You can go and check all 11,814 paths. I actually have done that. You know what I didn't do, but I should have done is histogrammed all the answers just to see kind of the distribution.
It's a great idea. Yeah.
Sorry?
Yeah, can you do that right now?
Oh, I'm scared to. Let me see. Did I call it values? No. What did I have to remember what I called it. You could tell me to look at my code, but I'm embarrassed to look at my code. Let's do it. Let's do it.
Okay. Okay. Hold on. Let me have a look.
Well, values is a local variable in here. That's why I don't have it handy. So, no, values is just along this one path. All right, if you want to think about it, well, I mean, it's hard to do that while on live television. I have it here somewhere, though. I must have it right here because the winner. All right, one more second, just for fun. Here's the winner num. I have to remember where I put it. I've asked the author of Pluto, and he's going to do it, which is going to, if you find a variable and then you want to know where it's defined, if you
winner num is right at the bottom, yeah.
There it goes. Okay, so so this is actually probably all I need, right? These are the values. Yeah. Yep, these are the values. All right, here we go. All vowels. Since you asked for it, I will do it. Might be fun to see. Okay, so
you're going to need to run plots.
And I've got plots. So what do? I just go, can I go histogram of all values?
Yep.
That would be fun. All right, histogram of all vowels.
What do you expect? Yeah, that's what I was about to say.
You were about to say a bell-shaped curve?
Yeah.
That's kind of interesting. Here,
it's not obvious. Yeah.
So what Dave is doing here, and this is completely not scripted, is computational thinking, right? You've got a computer in front of you. So why not just explore and play around and see what's happening?
Yeah, it should be binomial, right?
Sorry?
It should be binomial.
So does it look to others that's a little bit more heavy on the left than on the right, a little bit skewed? Can I actually calculate the skewness? Is that a word in Julia? I don't even know.
No, you.
I would have to load the stats package, right?
Yeah. Using statistics, true.
Right. Should I just do it?
Yeah.
See, this is computational thinking, where you play around.
Why do you say it would be binomial, Charles?
Because you're sort of at each point, you're this is of the
All the
this
paths.
is of the values, not of the
No, these are the sums along the path.
sums
Yeah.
along the paths, and the
Right.
sums, but the sums were chosen randomly, right?
The values are chosen.
The values are randomly.
Values are chosen randomly.
But there's no independence.
Right, because there's no independence. These paths.
I mean,
Right.
Yeah.
In fact, that the very point of dynamic programming.
I'm not arguing it's a binomial. I'm saying it.
I'll give you
like something
what I would have
that's
said.
binomial-ish. You know?
I'll tell you what I would say in Charles's place, which is that everything in the world is a bell-shaped curve, with high probability, right? That's just a sort of not a theorem, but an observation of nature, right?
But it's a shame we didn't guess that actually and say that before the picture.
Yeah.
Oh well, but is skewness a word in Julia? Now that I have statistics, I don't know if it's a or kurtosis. Anyway, these are the ways you measure these things. All right, we're going to get into a statistics module pretty soon, but that's not today. But yes, this is fun to see that there are all of these. How many did I say? There's 11,814 paths on an 8x8 square, and here's the distribution of all of these sums. And of course, the minimum right over here at number 7 is this little point way on the left, right? And there are all these other possible sums. Okay, but let me get back to the problem.
So are those all of the sums actually interesting in some way?
Are all of them interesting? I don't know.
I mean, is that an interesting question to ask? Sort of what is the mean sum, for example, or something like that?
Yeah, I'm sure somebody's thought about it. If not, there's a master's thesis to be had. Maybe if somebody wants to work on that. But it sounds like the sort of thing that probably someone would have analyzed. But it is true that if you take a computer science class that's focusing on the dynamic program, you would probably your mind would be so focused on the minimum. Probably that's sort of the real applied problem. Like, you're sort of like you're traveling from here to there, and you have restrictions, and so you need the minimum to minimize some cost in some sense. So anyway, that's what you'd be focused on. And
but it could be that you're picking up your Mario and you're picking up gold coins.
Right. But it's also possible that knowing about these other ones, the distribution might also be useful for some other purpose. I don't immediately know what that would be, but it would be interesting to know, where that could come up. But anyway, let's make sure everybody understands the problem. So we're taking all of the paths that can go south, southwest, or southeast, and we're finding the minimum sum as you go. Okay, and on an 8x8 square, like a chessboard, there's 11,000 paths. But if I go up to a 12x12, you see that there's already is this 15 million, right? I should have put the commas in. Is it 1.5 million? I think it's 1.5 million. 1.5 million. Okay, and these things grow quite quickly, exponentially. So the truth of the matter is, at a 12x12 square level, checking all the paths is actually not all that prohibitive. But at least with Julia, I'm not so sure about other languages. But in Julia, it wouldn't be that prohibitive to just do the naive thing. But there's a lot more clever things you can do. And to illustrate how clever you can be, here, let's go down to 6 just to sort of.
But like 30 by 30 would be prohibitive.
Yes, 30 by 30 would be prohibitive on any computer to do it naively. That is probably true. In fact, I think I was kind of scared to even go up to 20 when I was starting to play with this. And when you do this live, you want to be able to just sort of move along like this without any friction at all. So here, let's rather maybe an odd number might be nice. Here, let's go to n equals 7. Let's do that. Okay, so I'll make a 7 by 7 checkerboard, so to speak. And now what I'm going to do is I'm going to fix a point on my path, right? So I've got, with the scrubbable, I can actually take any point I want, right? I could take the 2, 6 point. And then now what I'm going to do is look at all the paths that go through this one point. You see, I've taken a subset of all the paths. Here, let's go to the middle because the middle's pretty. So here, let's go to the 4th row and the 4th column. there's a symmetry to that. So let's do that. Yeah. So let's look at all paths that go through the number 7. Okay. And so here I'm going to start stepping along, and you can start to see all the paths that go. Remember, you go south, southwest, and southeast at each step, and go all through the point 7. Okay. And you can see what they look like, right? I'm dancing along, moving around, right? You can see I'm just moving. In fact, let me do one other thing. Let's actually go through the points. Actually, let me go to the 6th row rather. Maybe that'll be even more interesting. And yeah, so here I am. I'm looking at all paths that go through this number 1. In fact, now that I look at this example, let's go. I've got too many 1s around. Oh well. Yeah, I've got way too many 1s here. Let's actually go to the one in the 3rd column. That'll be better for.
Could you zoom in on your notebook?
I will.
Yes.
I will make it nice and big. There we go. Nice and big?
Yeah.
Okay. So now what I'd like you to do is let's look at all the paths that go through the number 8. Okay. And let's see what happens. Well, if I go through the number 8, well, let's see. I hit 0, 1, 4. Okay. Oh, 0, 1, 4. The black moved. Watch the black above the 8. Okay, that's moving. The one after the 8, which is in blue, is going 0, 1, 4, 0, 1, 4, 0, 1, 4, 0, 1, 4. Do I really have to try? Suppose I actually looked at all the paths through 8. Just, do I really have to add them all up over and over again? I mean, this seems sort of silly. I know that the minimum is going to be the one with the 0, right? So why am I bothering calculating it 3 times when I know that it's good enough to use the 0, right? You see it, right? It's so the cleverer idea would be, well, don't repeat all of those 0, 1, 4s. Just do the 0. Well, now let's take that idea up a row. Okay, so let me actually go up a row and look at paths through the number 4. Okay, well, you're going to see that if you just look at the ones that follow 4, you're going to see sort of 9 things repeating themselves, right? I'm just going to call them 1 through 9. Here's 1, and oh, I have to click on this. 1, 2, 3, 4, 5, 6. You can see the pattern. 7, 8, 9. And then the pattern's going to repeat itself. 1, 2, 3, 4, 5, 6, 7, 8, 9. Right? 1, 2, 3, 4, 5, 6, 7, 8, 9. So you start to realize that once you were down here and you realize that the 0 was going to be the smallest, right? Let's see, which one of these was actually the smallest? I'm not even sure anymore, but probably this one here, actually, the 2, right? For this number 4, I'm pretty certain that the 1 and the 1 would be the smallest. So you see, of all these 9 possibilities, you could see it again. This is 14, 6, 7, 8, 9, 12, 2, 5, and 2. You get to pick which 2 you want. You could take this one or this one, right? The 2 is going to be the minimum. You don't have to look at all 9 possibilities, right? And then as you move up the chain, you start to realize that there's a much, much better way to compute the minimum rather than simply looking at all the paths forward. Instead, what you can do is you can work your way backwards, and you could see for every box, you could see what is the minimum below it, and the minimum below it will actually have the solution readily available. So you're going to see this again. I just kind of right now, I'm not spelling out the full idea. It's a little vague. You're going to see it again in a minute. But the key words are the idea of overlapping subproblems. I'd rather sort of get that main point into your heads right now, the idea of overlapping subproblems. When I did these 9 steps, from here to here, there were 9 overlapping subproblems. And so it's not necessary to repeat them each time, right? And as you go up higher, there'd be like 27. If you're getting the edge effects, there'd be 27, then there'd be 81. There's a factor of 3 each and every time that you don't have to repeat. Okay, and so the idea of dynamic programming is to somehow remember the subproblems so that you don't have to repeat these subproblems. So keep that in your mind. We'll kind of drill down at some point. But what I'd like to do next is give you a really cool application, which is the seam carving. And as I said, I'm going to show it to you quickly, and then we're going to watch this video from last semester that was just amazingly wonderful. I think you'll enjoy it, that talks about exactly this. But let me mention the idea of seam carving. So in fact, I'm going to switch for a moment. So there are a few images here, and of course, you know how to take your own. But I'm going to take the home of MIT's computer science. This is the Stata building at MIT. So if you've ever been to MIT, you'll recognize this very, very funny looking building. So this is a Geary building, which kind of has no right angles hardly. It's, you know, some people describe this building as non-Euclidean. Tourists come by just to walk down the street just to see this building. And in my own family, I have a 20-year-old son, but when he was 4 years old, we drove by, the building was probably brand new at the time, and we drove by and he said to me, "Dad, that building is broken." And so in my family, this was called the broken building ever since. But this is the State Center.
That's wonderful.
And
it's so true.
it is true. So let me cut to the chase at the bottom and tell you what the seam algorithm is going, the seam cutting algorithm is going to do. So at the bottom, let's go all the way down. Here we go. At the bottom, I have this slider, and what's going to happen if you look at on the right, we're actually going to cut out a path at every step. We're going to cut out a path that's just like the path I showed you in the dynamic program. This sort of lightning bolt in purple that's on the right here. At every step, there's a pixel that goes only south, southeast, or southwest. Okay, and it's some optimal path. And what it's doing is it's removing one pixel from the row at every step. Okay, so we could keep on going. And you could see what it's doing. It's actually compressing the image. It's reducing the number of columns. And so one original motivation for this is to be able to take an image that might have been designed for a computer screen and maybe display it on a telephone, right? Something with a different aspect ratio. And so what you'd like to do is somehow compress the picture, but not compress it by just, you know, chopping pixels off the edge or removing some pixels in the middle, but somehow removing the least important pixels by some measure, right? The ones, what you really like to do is remove pixels that somehow don't matter to the image in some possible way. Okay, and this is what the seam carving algorithm is going to do. It's going to do a dynamic program, and it's going to remove one pixel every time. Okay, and the way it does is it roughly what's going to happen, you'll hear about this in a second, it's going to look for these sort of lightning bolts that kind of have minimal changes to them. Okay, and just a small side story about this algorithm. I really love this algorithm. I first found out about this algorithm because, I don't know, maybe it was around 5 or 6 years ago. I was invited to a meeting in computer science where they were thinking about what language to use for the introductory courses. Okay, and they were talking about Python and a few other languages. And one of the questions that, Julia was still young at the time, and one of the questions that came to me is, can Julia do, what can Julia do? And I said, well, Julia will run fast. And so one of my colleagues mentioned this algorithm. I hadn't seen it before. And we went home and tried it. And the difference between doing this in, I'll just say language X, which is being used a lot these days, and being able to do it in Julia is incredible. So in language X, they took very, very tiny little images, and it took forever, apparently, to carve the seams. But in Julia, you could just do, this is running live. And so it's pretty fun to be able to do this sort of thing. I think it's running live. I have to check. But it's certainly very, very fast to be able to do this sort of thing in Julia, which makes it more fun, right? So part of computational thinking is to be able to interact in real fast time, and so you really see what's going on. Okay, I think that's enough of a sort of quick introduction. Now what I'd really like to do is just play the video. I'm telling you, you're going to, I could describe this algorithm, but I think that Grant was just did such a phenomenal job. And so I'm going to go to the video here. And I'm just going.
This week we are going to be talking about.
I'm just going to play this video. I'll put it on full screen. And this video is 27 minutes, and I absolutely think you'll love it. So please listen. Okay.
This week we are going to be talking about an algorithm for resizing an image, but without resizing the objects within it. So I've skipped all the way to the bottom of a notebook that you're going to go through this week. And what you'll see is we've got this very famous image, the persistence of memory on the left, all the melting clocks. And then on the right is going to be a squished version of it. And based on how I tweak this slider, we can squish it to be narrower and narrower. But if you'll notice, even as I get it to be about half the width that it was before, the clocks themselves haven't actually changed their width, nor has this weird monster-looking creature. Instead, the algorithm is smart enough to kind of kill the dead space inside the image without killing any of the content. And if you contrast this with how a lot of design software handles things, if I were to open up Illustrator and I take the same image and I say I want to rescale it, I want to make it half the width, it squishes all of the contents inside. It sort of deforms it. Other pieces of design software actually have different defaults. So if I were to go to Figma, for example, and I take the same image and I say, okay, let's try to rescale it, what it defaults to doing is cropping it. So it'll take out some of the content on the left edge. But if you want to somehow get the best of both worlds, where you're not getting rid of anything on the inside, but you're not deforming anything on the inside, this tactic, which is called seam carving, is kind of a shockingly effective way to do that. So I'm going to give the high-level view of how this algorithm works in this lecture and start to go through a bit of this notebook, kind of from the bottom to the top at first. And as the week progresses with the other lectures, we're really going to dig into the code for how this is possible. So the first step, I'm going to go ahead and change what's displayed here to give a little inkling of what's going on. On the right, you'll notice these sort of pink lightning bolts. What's happening is that with each step, as we're making the image smaller, the algorithm decides on a seam to remove from the image. So this is a set of pixels where there's 1 pixel per row that forms this continuous path from the top to the bottom. And it has to somehow decide what path is the one that's most okay to get rid of. So you'll notice right here, it's this path that's avoiding the branch, it's avoiding the clock, but it's just going through the sky and the ground. And it's saying that's probably something that we can cut out, and it keeps the image looking largely the same. And as I keep shrinking it further and further, it's choosing these other seams, which look like these pink lightning bolts. So the question is, of course, how do we find that? What is it actually doing? And the tactic here is going to be to assign some kind of importance to each of the pixels in the screen, and then find the path from the top to the bottom, which passes through the least important pixels. Or if we were to have a number associated with that importance, as you add up that number from top to bottom, it should be minimizing that total quantity. And there's different approaches that you can take, and the original paper on this describes several different ones. But what we're going to do, in conjunction with what we were talking about last week, is a kind of edge detection. So skipping up higher in the notebook here, we've got the same image on the left, and on the right, you'll notice that we've pulled out all of the edges into this really kind of pretty looking pencil sketch view. And what we're going to say is that the importance of a pixel is going to be the extent to which it sits inside an edge. So all of the white ones that we see on the right here would be considered important. They shouldn't be cut out. But anything black, so you notice that's coming from the sky, it's coming from the ground, all of that where there's not any sharp edges, those are the pixels that we're okay removing. Now, in the last lecture on
Alan, you can't mute yourself. Alan, we've lost sound. Alan, can you hear me?
is something that produces positive values wherever the blob image was fading from bright towards darker, and then negative values where it was fading from dark towards bright. And if that seems like the opposite of what you might expect, thinking of this kernel, remember that with convolutions, we actually think of turning that kernel upside down before it marches across. And again, this was all in the last lecture if you want to.
We lost sound for a while there. Could you
now instead, if we were to filter it with the other.
Did the sound get lost?
Yeah.
Should I go back like a couple of minutes?
Yeah, I think so.
All right, sorry, everybody.
Does
Would this
anyone remember
be a
when?
good place to go back to? Or
I don't. It was a bit before that, I think.
should I go back to the beginning of the segment? Maybe here?
Yeah.
All right, sorry, everybody.
Can you go back a bit further?
Sorry?
Go back a bit further?
I can't hear you. I'm sorry?
Can you go back further?
Go back further. Okay, let's go back further.
It was about there, I think.
All right, sorry, everybody.
Is a kind of edge detection. So skipping up higher in the notebook here, we've got the same image on the left, and on the right, you'll notice that we've pulled out all of the edges into this really kind of pretty looking pencil sketch view. And what we're going to say is that the importance of a pixel is going to be the extent to which it sits inside an edge. So all of the white ones that we see on the right here would be considered important. They shouldn't be cut out. But anything black, so you notice that's coming from the sky, it's coming from the ground, all of that where there's not any sharp edges, those are the pixels that we're okay removing. Now, in the last lecture on convolutions, I touched just a tiny bit on edge detection with Sobel filters, but let me switch to another notebook here to go into a little bit more detail on that. So I've got a very simple image here, which is just a white blob in a blue background. And what we're going to want to do is somehow pick up on all of the edges, which should just form a circle around it. In this cell here, I'm looking at the kernel library, and I'm calling Sobel, which, if you'll remember, pulls out two little 3x3 arrays. So if we were to just look at the raw data for one of those arrays, the one that I'm naming SX, you'll see it's a 3x3 array. It's got values 0 down the center column, and then positive values on the right, negative values on the left. And if we just pull up a simple function to visualize that, we're looking at it as blue on the right and red on the left. And if we look at the other one, SY, same deal, but it's just kind of pulling out from the top and the bottom. And now let's say we were to do a convolution with one of these filters. So maybe I'll take this one in the X direction. So a simple 3x3 grid, and I'm going to do this convolution against the blob image at the top, which, as you might remember from last lecture, means we sort of take this kernel and have it walk across every pixel and take a weighted sum. What we end up getting is something that produces positive values wherever the blob image was fading from bright towards darker, and then negative values where it was fading from dark towards bright. And if that seems like the opposite of what you might expect thinking of this kernel, remember that with convolutions, we actually think of turning that kernel upside down before it marches across. And again, this was all in the last lecture if you want to look at that with more detail. Now, instead, if we were to filter it with the other one, the one that was in the Y direction, and if I go and change what's going on down here, we see that it picks up on the top and the bottom. Now, I actually want to visualize this in a slightly different way. So what I'm going to do is, let me go ahead and hide this cell, and I will also get rid of this cell. Here, let's look back at the kernel in the X direction. And then what I'm going to do is look at a bunch of little vectors on the screen that indicate how strong is the convolution of this image with that kernel at various points. And then it gives a little direction to it. So at points where the convolution pops out positive, it'll be vectors pointing to the right. And where it pops out negative, it's vectors pointing to the left. And then if I were to do this in the Y direction, which would correspond to convolving with that SY kernel, same deal. Basically, anywhere where that convolution is positive, it'll be vectors this time pointing up and otherwise pointing down. And then the main idea here is going to be to add those two vectors together. So if I were to just take the ones pointed to the right, so just the ones pointed to the right, and I add them with the ones that are just pointing up, what we get are these ones that are pointing away from the brightness towards the darkness. And any of you familiar with multivariable calculus might find this very familiar notion. It's something known as the gradient, where if you have a vector that has an x component telling you how much a value changes as you move from the left to the right, which we might call the partial derivative with respect to x. And then the y component tells you how much you change as you move up and down, the partial derivative with respect to y. When you package those together, it gets you a vector that points kind of in the direction of greatest change. So often it's described as the direction of steepest ascent. And actually, in that sense, I should be honest that the vectors that you're seeing right now are technically in the negative direction of the gradient, because the gradient proper goes from the low values towards the high. It'll point from low to high, and this is doing the opposite. For our purposes, the direction actually won't matter that much. All that we're going to care about is the magnitude of the vectors that we're looking at. And the reason that it's defaulting to this is just because when you do the convolution with a Sobel filter, it flips that filter around first. So it's sort of doing the negative of what you might expect for the reasons that I talked about last lecture. Now, while we're here, it might be worth really digging into why this particular filter, this shape of values, is a reasonable way to try to measure something like a derivative, a partial derivative in the x direction or in the y direction. So if we go over and we just picture a grid of values, let's say we want to understand the rate of change around the pixels surrounding what I've labeled as E here. The first dead simple thing you might think to do if you want to know what's the rate of change in the x direction is to just look at the value of that pixel f and then subtract off the value of pixel e. And honestly, that would probably work. You could have an incredibly simple kernel that was just adding up the value to the right, subtracting the one to the left, and that would get you some notion of a partial derivative. But if you want more of the information in what's going on, you might also want to maybe average this or simply add it to the difference between E and D. What's the change between this pixel and what's happening just to the left of it. So we might add on, the difference between E and D and potentially divide the whole thing by 2 or average it. It doesn't really matter in absolute terms. All we care about at the end is the relative terms. What's the relative change around one pixel compared to the amount of change around another? And if you look at this, of course, we can just cancel out the minus E and the plus E going on. So it's just taking this right value minus the left one. And again, that would probably work pretty well as an edge detecting filter if all you did was take that F minus D. But with the Sobel filter, effectively what you're doing is taking a kind of average with what's going on the top row and the bottom row. Or at the top, we would be taking the same deal, but the corresponding terms are C and A here. And at the bottom, it would look like I and G. And really what a Sobel filter does is it gives more weight to this middle one, since after all, that's where the pixel we care about is. So it gives kind of half weight to the ones on the top and bottom, and then more weight to that middle one. And if you unpack what this is really saying in terms of where you add and where you subtract, it gets you exactly this shape that we were calling SX over here. And if you just look at its values, it's exactly what I just described. You're taking in that middle row something on the right minus the part on the leftmost, and then the top and bottom rows do the same, but scale down by a little bit. The whole point here, though, is that when we use those Sobel filters to get a notion of partial derivative in the x, partial derivative in the y, and that gets us a gradient vector, if we just look at the magnitude of that gradient vector, and I'm going to plot it down here where white means a higher magnitude, black means a lower magnitude, what we've done is picked up on the edge of this circular blob. And this becomes a little bit more interesting if we take something that's different than the disk and we have another very pixelated image like Mario in here. So here, again, we're doing the same thing where we have all of the rates of change in the x direction. We're adding them to all of the rates of change in the y direction. And then if we just look at the magnitude of those gradient vectors, it picks up on the edginess of Mario. And more than that, it tells us that the brightest pixels are the ones where there's a really sharp edge, and then the ones that are kind of a lighter gray are an edge, but ones that don't correspond to as much contrast. Now, digging into the code for what this is actually displaying, you'll notice that I've got a del x and del y being defined as the partial derivatives of this image. And that partial derivative function, as I've kind of been describing, is basically just applying Sobel filters. It takes the Sx and Sy, the kernel.sobel that we were just looking at, and depending on what I have toggled here, it will populate the del x term to be a convolution of the brightness of the image with the Sobel filter in the x direction, and then the del y term is a convolution of that brightness, but with the other filter. So that's all the partial derivative functions are doing, but this is just a nice abstraction so that we don't have to think of the convolution necessarily. And if I have both of my buttons toggled here to say, yes, we're taking into account the x and the y direction, what it does is it basically just takes the magnitude of that vector. It takes the del x direction squared, the del y direction squared, and then the square root of all of that. That is going to be the notion of importance that we assign to each one of our pixels. So jumping back to our Salvador Dali example, that's exactly what's going on with the image on the right. And if I open up a little under the hood here, you can see that. We're pulling out these two different kernels, the Sobel filters. We are taking a convolution, in this case with the brightness of the image, and then taking the square root of the sum of the squares of those values that's what's determining the value of each pixel. And if we scroll up a little bit, we can see kind of all of that broken down a little bit more. This image on the left is the convolution with the SX filter. The one on the right is the convolution with the SY filter. So kind of the edginess in the X direction, edginess in the right direction. But thinking back to our end goal here, which is the really clever way to shrink down an image by cutting out the unimportant seams, this still leaves an open question of what's the best way to find that seam from the top to the bottom? Find some path from the top to the bottom, which we consider to be passing through the least important of all the pixels. Well, for that, again, let me shift to a smaller example that might be a little bit easier to think about. Okay, so here I've got a grid and I've associated a value with each element in that grid. And let's say I want to start at this one, which is 0.3, and I want to find a path to the bottom that passes through the lowest valued pixels. Now, one approach might be a greedy algorithm, where we look at the three below it, and this is going to be our notion of connectedness, is that each pixel has to be connected to one of the three below it. You can't jump more than that. We can talk more about what might happen if you try. But if we take a greedy approach, you would just choose the one that's the lowest value. So in this case, it would choose the pixel with value 0. And then we look at the three below that. It would choose the one with 0.2. The three below that, the smallest is 0.4. And we continue on like that. And this would be sort of a greedy algorithm way of finding a seam down the image where the total value of all the pixels that it touches is pretty low. And in this case, if we add them all up, it ends up being 1.3. But the problem with greedy algorithms like this is that you can't be sure that you've actually found the best seam from the top to the bottom. And in fact, for this example, it's not the best. And we can see that with another much less efficient approach where we search through all possible paths from the top to the bottom, and then we consider the sum of the values that it passes through each one. And we're just going to keep track of which one is the lowest after searching through them all. So here, it searched through them all. In this small example, there were around, I think, 200 examples it had to search through. And it found one that isn't the greedy algorithm. Notice as it goes from the first pixel, from the first row down to the next row, it doesn't take the smallest choice. It takes that 0.1, because that gives it access to much lower values on the way down. And here it was a total of 0.6, in contrast to the 1.3 that we had from the other example. But if you start to think about computational complexity on doing a tactic like this, where we're searching through every possible path from the top to the bottom, remember, each step involves 3 different choices. So you're taking basically 3 to the power n, where n is the number of rows. That's going to be on the order of the number of steps that you have to take, which for any reasonably sized image is going to be completely untenable. But if we notice what's actually going on here, there's a lot of repeated computation in doing all of these. So for example, while it's searching through these paths, on this one, it has to add up 0.3 plus 0.0 plus 0.4 plus 0.0 on and on. And then on the next one, it takes pretty much the same sum, but it's only changing that last part. And then on the next step, it again has pretty much the same sum for the beginning with just changes at the end. So going through all of these and redoing that sum every single time is clearly pretty inefficient. There is a lot of room for improvement here. So the actual algorithm that we're going to use, which falls into a family of what we might call dynamic programming, will make an effort to memorize some of the sums that it needs along the way so that it doesn't have to recompute things needlessly. So pulling up the very last animation here before we jump back to the notebook, I'm going to have that grid of values on the left. And for lack of a better term, some people often just call these values the energy. So we're trying to find a path of minimal energy. And on the right, the goal is going to be to populate this in a way where each value will tell us the minimum possible total energy of some path towards the bottom. So for example, this 1.7 at the top is telling us no matter what path we choose to get towards the bottom, it has to have a total energy of at least 1.7. So, maybe it involves taking this 0.4 plus 0.4 plus 0.2 on and on. It's something that's relatively high. Whereas this little value here, that's 0.3, tells us there's some path from this pixel towards the bottom where the sum cumulative energy is 0.3. And looking over at the corresponding point, we can probably see what that path is. It's this 0.1 plus 0 plus 0 plus 0 plus 0.2. Now, as far as how we actually form this, we do it from the bottom to the top. So the first step is going to be to simply copy that bottom row, since once you're at the bottom, that's the best that you can do. Whatever the energy of the pixel that you're on, that's going to be the minimal total path. And then for each pixel above it, all we do is say, what's the smallest number below you? And then I'm going to add the new energy of the new pixel that I'm on plus the minimal energy below it. So, maybe I'll scoot over to a more interesting example like this one, where it's got 3 possible energies below it, 0.2, 0.5, and 0.3. Obviously, the step that it would choose to take is to get to that 0.2, and to get the new cumulative energy, we take the energy of that corresponding pixel, which is 0.2, and that gives us that 0.4. And so that's how we fill out that row. And then we do precisely the same thing for the next row. So let me jump to another maybe interesting, this is a sufficiently interesting pixel. So this one, we see that it's got 3 choices for where to hop below it. And now it's not looking at the energy of the pixels below it, but it's saying, once I get to that pixel below me, what's going to be the sum total energy of the minimal path to the bottom from there? So in this case, the best option would be this 0.2, and then we add that to the value of the pixel, which is 0, and we get that 0.2. So we keep doing this iteratively on the way up, and what it means is the number of steps required is just 3 times the total number of pixels in the image, which is dramatically better than the 3 to the n that we were getting by doing the exhaustive global search the inefficient way. But this still gives us a way of finding the globally optimum choice for a path from the top to the bottom. Because, for example, let's say I'm starting from the pixel we were looking at earlier, this 0.31. All I have to do is look at that, and with each step on the way down, simply go to the lowest. So I go to the lowest neighbor here, that's 0.3, the lowest neighbor there, that's 0.2, and keep doing that, and what I'll find is a minimal path, which you'll notice that 0.6 should be familiar from what our globally exhaustive search doing it the inefficient way ended up finding. After it looked through all of them and did all of these computations, it sniffed out the one that was, in fact, total energy 0.6. So that's what we might call the dynamic programming approach, where it's kind of keeping track of values on the way, not having to redo computations. And let's see what it looks like in the context of our notebook. So what we're going to do is look at each pixel and ask, hey, what is the path with least total energy towards the bottom? And in this context, what we mean by energy is the edginess of that pixel, measured with the gradient, like I was just describing. So if you say, hey, what's the minimal total energy for some path from this particular pixel towards the bottom, and then you assign it a color, this is what we get. So just to be clear, this image right here is kind of the scaled up version in the context of the melting clocks image of what we were building up in a much smaller example over here from bottom to top, where the pixels which are increasingly teal are the ones that don't really have a good path from the top to the bottom, so to speak. So over here in our notebook, everything which is a really bright pixel is kind of screaming out, do not touch me. If you have a seam that ends up where I am right now, there's going to be no way towards the bottom that doesn't involve cutting out things that we want to keep. So if we, compare this to the actual image that we have, you'll notice that we get these kind of triangle shapes above all of the content. So above the strange monster creature here, we have these triangles, which is a way of saying, don't let a seam get into this point, because once it gets there, any path towards the bottom of the image will have to pass through something which is full of edges, something which has high energy, something that we don't want to get rid of. You'll be going through more of the implementation details in the next lecture with a live coding session featuring the one and only James Schloss. But for right now, let's actually take a little bit of a peek behind the hood to see what's going on in generating this, this array of values, which again is exactly what we were looking at with this animation over here, where we're kind of going from the bottom to the top, thinking term by term, building up values based on just adding the energy of a given pixel with whatever the minimal term sitting right below it was. But let's think through that in more detail. So we've got this function here, which is trying to find the least edgy path, the least edgy values for a given array of energies or edginess or whatever we want to consider E to represent here. So we start by creating an array of zeros with the same size. And then we're also actually going to keep track of the directions. So what direction should we step from each pixel to get to that optimal path? That actually makes it so that we can draw one of these seams. Now, if you'll remember, the very first step before we did any of the recursive looks was to copy whatever the bottom row in the energy matrix was over to this new one that we're generating. And so that's exactly what we do here. We take whatever that bottom row is for E, and we fill that into the least E matrix. From there, we have a loop that goes from the bottom to the top, and then we're going to go from the left to the right. And essentially what we're doing here is we're just finding the minimal value from the least E matrix that we've already been building, and then we add that together with the corresponding energy value of the original matrix. And then what we're also doing is keeping track of the directions. So for example, if we were to pop over here and we imagine while we're populating this, we're populating, let's say, yeah, this pixel here. So it looks at the 3 below it, it sees that 0.2 is the smallest one. We want to remember that that's the direction it's going to walk. And so here we're going to assign an index of -1, 0, and 1 for the 3 possible directions that you can step as you go down. And we're filling out this matrix of directions, what we're calling DIRs. And what this line says is essentially fill it either with a -1, a 0, or a 1, depending on what the minimal value that we found was. So once we've built up this matrix of directions, we could actually visualize it with a bunch of little arrows if you wanted. So this is what comes out from a sub portion of the Salvador Dali image, where we're stepping either a little bit down to the left, a little bit down in the pure direction, or down to the right. And that effectively is the same as having seams for our image. So over here, we've got another little slider, which is basically telling us what is the best possible seam from a given pixel on the top towards the bottom. And it's using that directions matrix. And you'll notice on the right, what it's passing through are all the darkest pixels, right? It's the ones that involve low energy. So as we kind of play with the slider and walk it across, it's showing us the best paths from top to bottom that hit low energy pixels, which again means hitting ones that don't have edges, which is the metric that we're using for whether or not we want to include a pixel. And so that effectively is the algorithm. Once you have these seams, you choose the seam with the smallest possible energy, and with each step, you snip that out of the image. And as you snip more and more of them out, we get a narrower and narrower image, but it's kept all of the content. Now this works particularly well for our melting clocks image, but I want to show you an example where this fails. What are the times where cutting out the non-edgy pixels might not actually give us something that's visually what we're going for? So I think one good example here would be looking at Starry Night, because just based on the style of this painting, all of the stuff in the background, pretty much all of the things in the image are edges. There's a lot of changing in color as you move a little bit from point to point. And we can see this when we do our 2 different filters and compute our 2 different gradients. In this case, it's just tons of edges left and right. And when we put them together to get our pencil sketch, we see that the background, the sky, is full of whiteness. It's full of high energy things that we would potentially not want to remove. So when we build up that matrix with our dynamic programming approach that says, what should I not be touching? Almost everything in the sky in that actual background, it seems to want to avoid. And the one region that it seems okay going through is what actually sits more in the foreground of the image, this sort of bush figure. And when we actually apply the seam carving, you can see that in action. We can see how the slices that it wants to take out disproportionately include that dark foreground image simply because it has fewer edges than a lot of the things in the background. So for something like this, the performance, it still produces something pretty, but maybe it's a little bit less impressive if our goal is not to distort the objects within the image. But that doesn't mean this whole algorithm is out the window. What it means is that the energy function that you're assigning, the way that you're putting importance to each pixel might need to change, but then you can apply the same basic idea of finding.
Okay, so in the interest of time, I mean, we're actually almost done with this video, but I think I'm just going to sort of artificially bring it to an end. But I will, if you do get a chance to listen to it yourself, it's in the notebook so you can see it. There are a number of, granted, it's a nice job sort of picking things out from the paper to see what would happen if you tried some alternative algorithms. Like just pick out sort of the maximal pixel per row, and you'll see that you get these sort of strange effects. And then there's this really fun thing that comes up in a little bit further, where if you assign certain weights to, for example, a person in an image, you can actually remove that person from the image in a way that barely looks like you've removed any of the other content from the image. And last semester, there was an example of somebody out there on the internet who took our code, our Julia code, and reproduced exactly this phenomenon and kind of melded it to us. It was pretty fun to see. So we do have the notebook, as you know, to try these things yourself. And so I absolutely encourage it. And I think the last kind of message I'll say is, there are a lot of ideas here. There's dynamic programming, minimization, there's gradients. One thing I will mention, and let me see if I could find the picture, maybe it's further up. in terms of computational thinking, I mean, a typical multivariate calculus class where you learn words like gradient would never actually show pictures like this. But to me, this is like the most terrific way to learn about gradients. I mean, here you could see that this is the Stata picture again, and the horizontal gradient picks out the vertical edges, as you could see so well, right? And the vertical gradient picks out the horizontal edges, right? And you sort of put the both together and you get the biggest gradient. And boy, isn't that a really cool way to think about gradients as compared to what might be done in certain math classes.
Can we visualize that as a three-dimensional surface?
I don't know. I hear people say that humans are not good at 3 dimensions.
No, but now we've seen it in 2 dimensions, and it might, give a useful point of view to see.
I feel like I should get those like red-green glasses, those polarizing glasses, and look at the 2 pictures at once. Now, but yeah, that could be pretty fun. Having said that, I think now what I'll do is thank the viewers out there in internet land, and we could stick around a little while for the MIT folks if people wish to continue to stick around. But can I do this, or Dave? I think again, once you log